Hello everyone, my name is Jacob and today we're going to be talking about nucleophiles, electrophiles, arrow pushing patterns, and reaction mechanisms. So first off, we're going to start with the characteristics of nucleophiles and electrophiles. We'll start with nucleophiles. So nucleophiles are a species that is rich in electrons. They all have a pair of electrons they can donate to form a new covalent bond, which makes them Lewis bases since they donate their electrons. Pi bonds are also nucleophiles, and we watch for negative charges since negative charges are attracted to positive charges, and nucleophiles like positive charges. So on the other hand, we have electrophiles, and electrophiles are a species that is electron poor. They accept electrons to form new covalent bonds, which makes them Lewis acids since they accept electrons. And we watch out for positive charges since electrophiles like negative charges and positive charges are attracted to negative charges. So here we have some examples of some nucleophiles and electrophiles, and I can tell that this side has the nucleophiles because we have some electrons here, some lone pairs we can donate, and the oxygen is partial negative and the hydrogen is partial positive due to the differing electronegativities, and we know that the electron density will be going this way. So we know we got a nucleophile, and then for this chlorine we have a negative charge. We know that's a nucleophile, and this alkene has a double bond, a pi bond, so we know that's a nucleophile. And on the other side, for the electrophiles, we know that boron is partially positive from the electronegativities, so our electron density is going this way towards the fluorine away from the nucleus, so we know that it is an electrophile. And for this carbocation, we instantly know that it's an electrophile. We got a positive charge. And the aluminum trichloride is the same thing with the boron trifluoride, is that aluminum is partially positive and the chlorines are partial negative.
Hello everyone, my name is Alexa and I will be presenting what is a reaction mechanism and the different ways that this can be shown. I know Jacob showed what were nucleophiles and electrophiles and the significance of those because they play a big role in this next part. And so, what is a reaction mechanism? In organic terms, a reaction mechanism is a formalized description of how a reaction takes place, how we get from reactants to products. Similar to road maps or signs given to you while driving, reaction mechanisms show the direction of electrons as they make or break bonds. Now there are 4 different ways that this can be shown. 1 is nucleophilic attack, 2 loss of a leaving group, 3 proton transfer, and 4 rearrangements. In the next few slides, I will go into more detail on each of these 4 categories. Alright, so the first way we can show electron movement is through a nucleophilic attack, in which a nucleophile attacks an electrophile. And the best way I can show this is through examples. So this first example here, we have a negatively charged chlorine. It's going to attack the positively charged carbocation here. Now this chlorine we can label as a nucleophile and this carbocation as the electrophile. This is going to form a new bond between the chlorine and carbon, which is common to see in nucleophilic attacks. And is what we want because chlorine is more happy with 4 bonds. In this next example, we have a negatively charged iodine and is going to attack this carbon center here. Then, as a reminder, carbon can't have more than 4 bonds, so we're going to have to draw a second arrow to the oxygen to then give it this negative charge, and which is good because this will promote more resonance throughout the structure. And again, the carbon is happy because it has 4 bonds instead of 5. So these both show nucleophilic attack, and again, that's when a nucleophile attacks an electrophile, often to form new bonds that hopefully are more stable and promote resonance. To show electron movement is through a loss of a leaving group, and in most basic terms, a group is lost, or an atom, and the best way to show this is through, again, examples. So the first example, the chlorine group, is going to be lost, and the way to show this is through an arrow from this bond to the chlorine atom. This will leave chlorine by its lonesome, and it will be negatively charged, and this will form then a positively charged carbon, or a carbocation, because again, carbon's only bounded to 3 bonds instead of 4, which gets that positively charged nucleus there. And in this next example, we will show the same thing. So this bond will be going to the bromine. The bromine will be left by itself with a negative charge, and then this is going to form again a carbocation, because the carbon is losing a bond and therefore only has 3 bonds and will have that positively charged nucleus. So I guess to identify the loss of a leaving group, you will always see just one atom hanging out by itself, often with a negative charge, because it is lost from the original structure. All right, so the third way to show electron movement is through a proton transfer, and that is a reaction in which a proton, H+, is removed from one species, the acid, accepted by another species, the base. It requires 2 curved arrows. So this first example, we are going to be removing a hydrogen from this species and donating it to this species. And to show this, we draw the arrow from the oxygen to that hydrogen. Now, this is when it requires at least 2 curved arrows, so you can't forget to draw this arrow from this bond to the oxygen. Now, to identify the base and acid in this reaction, so again, the base is the one that accepts the hydrogen ions, and in this case, this is going to be accepting that hydrogen, and so therefore this is the acid, which is going to donate the hydrogen. So this is going to form a bond between the oxygen and hydrogen, and this will be positively charged because the oxygen will have 3 bonds. And then this is going to actually form water. So one thing about a proton transfer is, in these reactions, is sometimes it doesn't show the water forming, or the water in the second part of the reaction, and don't be scared if you don't see that. Sometimes it's just not drawn in, but don't think that it's not a proton transfer because of it. So in this next example, we have a hydrogen and an oxygen. So this oxygen is going to come in and take this hydrogen away. So this is going to be the acid then in this reaction, and this is going to be the base as it accepts the hydrogen ion. And this will, and I almost forgot to draw the second arrow. So this is going to this bond is going to come onto the oxygen here. Don't forget that, as I almost did. And so this will form a positively charged oxygen, as it is now bonded to an oxygen, or to the hydrogen here, and forms that bond. Plus now it's going to be HSO4 minus, as we have to add those oxygens together on this reaction. And this are 2 examples of a proton transfer. And just to go over again, an acid donates a hydrogen ion and a base accepts a hydrogen ion. So, and don't be worried if you don't see water forming in the product, as sometimes that's not drawn in. Right, so the fourth way electron movement can be shown is through rearrangement. And now there are many types of rearrangements. that can be shown, but we're just going to keep our focus on carbocations. And again, carbocations we saw before is an ion with a positively charged nucleus. And carbocations have an MdP orbital and therefore are stabilized by neighboring groups through slight orbital overlapping called hyperconjugation. So the more carbons around carbocations, the more hyperconjugation, and hence the more stability. So we really want more carbons, just look for that. And so that's why that this methyl group is the least stable, because it has no carbons around it, no overlapping occurs, no hyperconjugation, so therefore it's the least stable compared to, say, the secondary or tertiary being the most stable as it has the most carbons around it, a carbocation. And we're going to go through 3 different ways that carbocation shifts can occur. Carbocations can rearrange in a few ways. The first way we're going to talk about here is a hydride shift, which is essentially how it sounds. A hydrogen is going to shift to the positively charged carbocation, and like this has been labeled, this is a secondary carbocation, and we are going to make this into a tertiary carbocation as the hydrogen shifts over on this direction to this direction, and this new bond is actually formed, and this becomes now the positively charged carbocation. Now you may wonder, like, why does that happen, or why do we do that? Well, we want to make this again more stable, and it is more stable with the carbon on this side, as it now has 1, 2, 3 carbons attached to it, which again promotes that hyperconjugation and more stability, versus this one has the positively charged over here and it only has 2 attached to it. So that's why we want to do that hydride shift. Similarly, we are going to do the second way is through a methyl shift, and it's similar to the hydride shift, and we're going to move that to the positively charged anion there. And this is a secondary, and we're going to make it into a tertiary carbocation. So this is going to form into this. And again, the new bond is formed on this. So this is a CH3. And the positively charged anion is going to come over here. And this is going to form a tertiary because there's 1, 2, 3. So a tertiary carbocation. And again, the reason why this is a secondary is because there's 2 carbons. And we want more hyperconjugation, more carbons attached to this carbocation, so that's why we have that methyl shift. The third way the carbocations can rearrange is through a ring expansion. So this bond right here is going to attack this, or the positively charged anion, and this is going to form this. So it's now going from this box looking structure to a 5 carbon structure, and this bond, essentially this new bond is formed here, and the positively charged moves to right here. So again, this is forming a tertiary carbocation, is now 1, 2, 3 carbons, and before it was just 1, 2, which is a secondary carbocation, so we can label that tertiary. All right, so to sum up a rearrangement, we are going to do one final example, and we're going to look at this example here. So we see that there's a carbocation located right here, and we're going to label this a secondary structure because it has 2 carbons attached to it. So we want to make that more stable. And so we are going to do a hydride shift through this hydrogen here. It's going to come in and attack this carbocation to form a new structure, which is this structure. And the carbocation is going to move up here since the hydrogen shifted down. And this is going to make it a tertiary structure because it has 1, 2, 3 carbons attached to it, forming more hyperconjugation and more stability ultimately, which is what we want in rearrangement. Alright guys, so these are reaction mechanisms, and in just simple terms, this is how we get from those reactants to the products. And there are 4 different ways electron movement can occur, which we went over. And Jacob in this next part is going to go into how it is common to see more than one reaction mechanism within just one problem. So it is important to be able to identify these 4 ways in order to get the most stable structure and get the most out of each problem. I hope this video helped you, and thank you so much for watching.
So here's an example of a reaction mechanism, and this is a 7-step mechanism, and we can ID every single arrow pushing pattern in this mechanism. So the first one is a proton transfer because there has been a hydrogen added to the second molecule from the first, so we must assume that a lone pair from this oxygen completed a proton transfer. Our next step is a nucleophilic attack because we can see that this was added on to this molecule, so we're going to assume it's a nucleophilic attack and an oxygen's lone pair attacked this carbon. So our next step is a proton transfer. We can see that because this hydrogen is missing from this molecule, so we can assume that this lone pair on this B completed a proton transfer. Our fourth step is also a proton transfer because we can see that a hydrogen was added to make this water up here. So we can see that this lone pair up here from this oxygen did a proton transfer. For our fifth step, it's going to be a loss of leaving group and the loss of our H2O. So we're going to assume that this bond went into this oxygen and that we have a double bond right here with oxygen and carbon. So we're going to assume that one of these lone pairs on oxygen went into this bond to make that double bond. So our next step is a nucleophilic attack because we can see that this OH right here is from down here. So we can assume that a lone pair from this OH attacked this carbon up here. And then our last step is a proton transfer. And we can tell because this hydrogen is missing from the next molecule, so we can assume that this lone pair completed a proton transfer.